Bismillahirrahmanirrahim. Welcome into the special episode of Vector Space Model to all the viewers. Before that, we had a video about the theoretical concepts of the vector space model, that how vector space model works, what are the basic steps in creating a vector space model. As we are well aware that vector space model is very much helpful for search engines. It is basically a representation of our corpus data or our documents. We have a bunch of documents and we pass a query, and resultantly we get our relevant documents. For that we must have a vector space representation so that we may calculate our desired similarity. So let's move toward the next slide. We have few slides, then after that we have the implementation. For Python, we will use, for the implementation, we will use the Python programming language. It is basically used for machine learning and deep learning tasks. And for Python, we have many IDEs, integrated development environments such as PyCharm or Jupyter Notebook, and as well as Google Colab for Python. So we have PyCharm, but we will use Google Colab for our own convenience. Google is an online runtime for Python powered by Google, and it provides a GPU and TPU and have some good amount of RAM and a temporary hard disk or space to store your data. So Google Colab is quite very helpful here. So inshallah we will implement on Google Colab the vector space model. So first let us see the basic steps how we will implement this in Python. So first of all, we will load the corpus. We will load the corpus, and then we will pre-process the corpus data. As in last lecture we have discussed that before passing it to the system, we will pre-process the corpus data, that is removing the stop words, removing the punctuations and stemming, and all these processes are necessary, which is called a pre-process. Then we will have to fit and transform to TF-IDF vectorizer. We have a built-in sklearn library in Python to convert into a TF-IDF vectorizer, so we will use for our own convenience, but it is not recommended to use the built-in packages. But inshallah in coming lectures we will have a manual implementation of how to calculate the TF-IDF vector. So for now we will just use the sklearn. After that we will use the transform our query as well into vector. We will also perform some pre-processing task on our query, and then we will convert it into a vector. After that we will calculate the cosine similarity. Once we calculated the cosine similarity, we will have the relevant set of relevant documents, or the order in which document is more relevant and which document is less relevant. So let's implement the vector space model now using Python. Just visit colab.research.google.com. This is an online runtime powered by Google. So let's move towards our browser to open this link. We have already written the code for our convenience so that we may perform this task rapidly, because we have a 15 minutes limitation by the YouTube. So first of all we will load the corpus. Here you can see that we have a package. We have loaded a package sklearn feature extraction text and TF-IDF vectorizer. After that we have a corpus. We have defined here our custom corpus. It can be in the form of file, in the form of txt file, in the form of CSV file, in many other forms, but for our own convenience we have taken 7 documents for our experiment. So you can see that the first document is related to artificial intelligence, the second is about science, the third is about physics, and the fourth is about algorithm in mathematics, and the fifth is about chemistry, scientific discipline, and biochemistry and sociology. So we have taken documents, line of documents from different disciplines so as to experiment in a good way. So we have a vectorizer, TF IDF vectorizer, which we have called in the very first line. This TF-IDF vectorizer is a built-in function of the sklearn. So it will automatically vectorize our document. We need not to define the length of vectorizer. We will just fit and transform into corpus, and it will automatically generate our TF-IDF vectorizer. So in coming days, inshallah, we will perform this manually as well, and that will be might be a live stream, because it will take a lot of time to code manually the TF-IDF vector. For now, we will just have a built-in function. So after that, we have a vectorizer dot fit dot transform the corpus which we will fit into this vectorizer, and resultantly we get the x, and we have vectorizer dot get feature names. Features are the terms or the words, the unique words which are in this corpus. So let's run this code, this notebook code. So we have this features. We have this feature without pre-processing. So here we have 7 documents and 75 terms or 75 features. Okay, so this is row and this is column. So sometime row may represent the terms or column may represent the documents, but here rows are representing the documents, whereas columns are representing the terms or the features, the words which we have, such as algorithm, along. These all are the features. So now let's move towards, let's fit, because it is a very sparse data, so we will use a pandas data frame. This is a library of a pandas data frame that provides you to fit your data and to view it data, because if you call X to view directly, you will not be able to view it directly, because it is a very sparse data, means it is a very huge data and it can't be loaded directly. So we will load it into a pandas data frame, and in pandas data frame, vector2 array and column, we have vectorizer get feature names. So features as a columns. Okay, so we will just run this code, and we will find this data frame. So you can see that we have 6 documents, and in columns we have features. These all are 75 features. Everyone can see that these 75 features, against every feature we have a certain value which shows it is that its term weights, term frequency, TF-IDF weight. So basically these are the TF-IDF weights. This is the document 0, document 1, document 2, document 3, and so on up to document 6. So against every document we have the TF-IDF vectorizer. So this is basically a form which we desired, which we are desiring. This is a TF-IDF vector. So basically this is a vector space, and this vector space is very useful, so that in coming steps we will have a cosine similarity. But before performing the cosine similarity, let it pre-process the data, because this is data and this vector space is not pre-processed. So let us first pre-process. For pre-processing, we have to load this certain basic packages. For natural language processing, we have an excellent library, that is NLTK, for natural language processing, and this pickle is unnecessarily loaded, so we will remove it. So NLTK.download PU and Punkit, and NLTK download stopwords. So we will download the stopwords and Punkit. These are the 2 packages: Punkit for the word tokenizing and stopwords for loading the stopwords, and then we will set it into English. So let's load this set of code, and the concerned packages has been loaded with the data, and now we will set the stopwords as English. Okay, so stopword, let's play this stopwords. You can see that set stopwords words we call only English stop words, because it is a library. It contains many stop words of many languages such as German, French, English, Russian, etc. So these are the stop words. These are the stop words, and stop words are those words which are not much meaningful. So that's why we try to omit. So we have a list of stop words, and in coming section we are going to pre-process. So first of all, we have the pre-processing function. The very first pre-processing function is the tokenized the list. So we will tokenize means we have a raw text, and we will tokenize every term separately, means we will separate every term. So we have a built-in function nltk.word tokenizer. We will pass the word document text, and in return it will give us a tokenized tokens. Okay, so tokenized words. So after that we have another function. We define a function in Python like this, def word stammer like this. So we will pass an argument, that token list. The token list, for now stammer, we have a Potter stammer. ltk.stem.potter stammer is a stemming. The stemming refers to reducing the words into its very simplest form. Okay, so you will see how an LTK stems the words. For example, we have a word science. For science, it will omit the last e. For example, called, it will remove it into call, only call. So called will be stem into call. So removing stemming, for stemming we are actually our goal is to reduce the vocabulary. So once we reduce the vocabulary, we will generate good results. So we have a stemmed empty list. We are searching within the tokenized list which we have passed here. For every word we append that stem word. So ps dot stem, we have a stemmer, we call it a ps here. So ps dot stem words, it will stem every word and append it to an empty stem list which we declared over here, and appending every stem words, and after that the stem is being returned. Stemmed word list is being returned. And now we have a removing stop words function, very important function. For we passed a document text, we declared a clean text empty list, and we are searching within the document text for every word, and if word not in stop words then append, otherwise don't append. Okay, so if the word is in stop words, so do not include it into our cleaned text. Okay, so if it is not in stop words, then we are appending. So we have put here a condition not to include the stop words, just include otherwise the stop words. So it will generate and it will return the clean text to us. So these are all the functions which we have, three functions we have defined. Now we will use it, try to use it for a single document for our own cross check like. So we will just run this code. First of all, we can see the tokens we call the get tokenized list inside our corpus. This is our corpus. From corpus we have loaded the document 1. So document 1 we have loaded, and now we will print this token, and after that we will remove the stop words from these tokens, and then we will print over here. And after performing the word stemming, now see the word stemming we call the word stemmer which we have defined above this our custom function. So this custom function will stem the word. We will pass the document text which is already removed by the stop words. So these texts are now being stemmed. So let's run and check whether how it works. You can see that word tokens. Now we have provided it a raw text, a complete raw text, and now it has tokenized every word, and every word is being tokenized. And after that we have removed the stop word. You can see that and is these are the stop words which are not included, others are included. And in the third line you can see that these words are now stemmed. So you can see the experimentation is stamped into experiment, calculation to calcul, and observation to observe, and call to call, and science into science with E is omitted. So the basic purpose of pre-processing is to reduce the dimensions. Before we have 75 features, now we will see how much it will reduce now. So before passing it to a TF IDF vectorizer, we will use this joining function, because in for us now we have in this format, in tokenized format, we because tokenized format is not accepted by TF IDF vectorizer, so we will reconvert it into the raw text, means into a plain text. You can see that now the same line above line is a plain raw text without being tokenized. Okay, so now it is a single document experimentation for our own check. Let's perform on all 7 documents which we have loaded the very first. So we have a clean corpus. We now we are using an empty list clean corpus, and we will iterate over every document in a corpus, in our old corpus, the very first, the initial corpus, and in for every doc we will tokenize the list, and these tokens are being passed to the remove stop words function, and it will remove the stop words, and that text is now further provided to the word stemmer, and it is being now stemmed. So now this stemmed list is being provided to this code, and this joining code will remove will put every word and a space, and it will convert into a raw text, rather than a tokenized. So we are de-tokenizing our sentence list over here. So de-tokenized, and then clean corpus dot append, we are appending every pre-process data into our new clean corpus, so that we can pass into our TF IDF vectorizer. Now we have the clean corpus, we have appended every document, we have cleaned every document, and now we have a cleaned corpus. So after that, this clean corpus, we have we will provide this into a vectorizer. Okay, we will transform. So vectorizer dot transform clean corpus. This we called earlier with simple corpus. Now we are calling it with our clean corpus. We are transforming it into a vector. So now we will also print features names, means the vocabulary size or vocabulary or the features or the terms, and doc vector dot shape, we will find the shape as well. So let's play this set of code, but before yes, we have so as we have let's play this one first of all, then we have this corpus. Now you can see that we have now this cleaned corpus. Now we have this cleaned corpus, and now we will transform into vectorizer. You can see that why it has not reduced the vocabulary, because we might not let's pause for a minute. Now you can see that we have used a separate vectorizer for this. We call it a vectorizer X, and TF IDF vectorizer X. We have fit it into a clean corpus, our new corpus, and then we transform into a cleaned corpus. We get the features. Okay, so now you can see that before we had 75 features or 75 vocabulary size, but now it is reduced into 65. That is by removing the stop words, we have reduced our dimensions. So the less you have the dimensions, the better will be the results. So let us replay it again for the results. Should compile once. We can see that we got the shape as well, and we got the vector. So let's move forward and see the new transformed vectors. Here is the problem. We put into a vector x dot get features because we have a new vectorizer. We call it a vectorizer x. Now you can see that we have all 6 documents, but our vocabulary the stop words, and as well as we have stemmed our words. So you can see the values against each and this is our new vector space. So now we will perform some pre-processing on our query and transform into vector. We have a query physics and science. For example, we can place here, for example, we are searching for computer science, and let's see what result comes. And in computer science, we tokenize this query and then remove the stop words if any. If not, then okay. And then we have empty list queue, and we will search for every word in the query, every stemmed word. We have already tokenized, just we have not stemmed. That's why we are directly stemming here, and also providing it as a connection to the loop so that it will go for each word. So we have 2 words, it will run 2 times for computer and science. So it will append every word into queue, and then queue is retokenized, means detokenized into a raw text, and this raw text is being passed to vectorizer dot transform. So we will pass it to our new vectorizer x dot transform, and then we will run. We will provide the list of queue. Okay, so but not tokenized. Okay, so let's say why it is so slow. Can't understand, because we are only running the Google Compute Engine. We are not using the GPU. If we have used the GPU from the setting, it would have run very fast. So now move forward, and we have a cosine similarity formula. In cosine similarity, you can see that we have a kind of a dot product. We will multiply the query and the LLM and the expected every document, and then we will take the square root and sum of the square of every document. So this is you can expand this formula, but we have a built-in function cosine similarity. So we will call from sklearn.matrix pairwise import cosine similarity. So this is a built-in function you can implement at your own. In coming lectures, inshallah, we will manually implement this as well, and we will explore this formula manually. So how to it is very vivid here as well, that how we are taking the product and taking the sum. So resultantly we get the cosine similarity measure. So cosine similarity we call the cosine similarity measure. So doc vector, which we have the vectors of documents, and then a query vector. So it will check for every document in our vector space which we have shown above, and then we flatten this for any kind of errors. So let's run this code as well. So resultantly we get the cosine similarity, and the next step is we get the indices from this cosine similarity. So we have a built-in sorting function for cosine similarity, arg sort. It is a numpy function which will sort. You can go through that how to sort the numpy array. So we are sorting the numpy array and putting it to a related docs indices, and we will print it as well for our own convenience, and we will iterate over this indices and check in the clean corpus, and we have got the indices. This indices is important, and this shows that where the relevant document is. So it will point out the indices which the document which is more related, and then the less related, and then so let's run this, and we will see. You can see that this is our indices. So it is pointing out, first of all, for computer science, the third indice, then 0 indice, 1, 5, 6, 4, and last 4. So we can see it has loaded in mathematics computer science algorithm. So for computer science, it has given the highest cosine similarity to the algorithm document, and then the computer science and artificial intelligence, and then the experimental calculation, and then biochemistry and other. So the all other have less similarity. The highest similarity is of these two documents and these three documents. We can say the highest similarity is of the first document and as well as other documents. So the highest the similarity, the more relevant the document is. Hopefully this tutorial will be very helpful for you people. If there is any question, please comment down below, and please subscribe my channel for the on time lectures, and press the bell icon as well. If this lecture is above 15 minutes, it will be in different parts. So signing off. Thank you, inshallah, next lecture.